Hello class, this is CSE-5250, sections 2 and 60, week 15, spring 2025. Before we begin, I need to bring up an issue that was brought up to my attention. Depending on the platform you are compiling your trapezoid rule program, it might not show the prompt enter A, B, and N. If this happens, you just type it in anyway, and when you do, the prompt will enter after the fact. It's a little bit weird, and unfortunately, I do not have a good answer to this. It might be an issue with printf. I'm not sure if you need to swap that for something like cout, and if you do, it would have to be a C++ program. But anyway, that is an issue that was brought up to my attention. If it looks like your program is hanging, if it looks like there's no input, see if you can type in the values for A, B, and N, and then press enter. So anyway, that's the one issue in regards to the trapezoid rule program. So now let's go back and talk about your final project. So as before, you're going to benchmark your program. You are going to make a few minor changes to your program, however. If you have the program from Programming Assignment 2.5, the one where you made that pi estimating program based on dart throws, you're already halfway there. We just need to make a few modifications. But before we even do that, just in case you are running your program on a different platform, or if you've made changes to your previous one, double check the number of CPU cores on your system first. Same instructions as before. Alright, so here's the rewrites I am talking about. We're going to be benchmarking the pi estimating program that we made in the previous MPI assignment, the one that is based on dart throws. For ease of benchmarking, instead of changing the total darts to throw, which we had hard-coded previously, and then having to recompile it again, we're just going to enter it as a command line argument. So, for your first change, and I have a copy of our pi estimating program over here. Let's open that real quick and start editing it. I'm going to make another copy just for reference. We are working with this file here that contains all of the to-be modified code. Okay, so here in int main, add int argc, comma, character, star, argv, square brackets. Okay, now it's ready for accepting command line arguments. We can just type in our number of darts as part of our command to run our program. That also means we need that function that parses a command line argument into an integer value. See this 1 million here? You may have set it to a different value, but it is the total darts to throw. The right hand side, replace that with strtol argv1 null 10. There we go. So now, when you run your program, you'll be using this command here. MPI exec -n, the number of processes, / program name, and then the dart count. I'll show you what that looks like in a little bit. Let's continue with modifying this program. To make it easy on us for benchmarking, MPI has a function called wtime that is used to return the current time. So if we get the current time at the start of the program, and then get the current time again at the end of the program, if we take the difference between those two times, we get our runtime. So MPI wtime is an MPI related function. That means if we want to use it, it's got to be after we call MPI init. So let's just, for convenience, we'll related functions. Our timekeeping related variables, we're going to define them after MPI init, MPI com size, and MPI com rank. And right before all the other work, we're going to add the following lines of code before we seed our random number generator. So start and stop, those are our start times and stop times. We are having process 0, only process 0, work with these two variables. So if my rank equals 0, start equals MPI W time. Why process 0? Because process 0 is the process that's waiting on all other processes. So every process is gonna get the same total darts to throw. From that, it's going to calculate its own local darts to throw. Then each process is gonna throw their own share of darts. All processes do a reduce operation where process 0 gets the total number of darts this way, the total number of darts thrown within the dartboard, and then it's process 0 that's going to calculate the estimated value for pi. So again, it's process 0 because process 0 is the one waiting for all other processes to complete their work. Process 0 is also doing work. It's just that it's doing work at the same time as all other processes, plus gathering, or rather, doing the reduce operation to get all of these dart values into process 0. So now that we have start here, now that we have the variable start set to the current time, let's go towards the end of the program and calculate our stop time. So I'll add it to this block of code here. If my rank is 0, we're going to print out the estimated value for pi, but I'm also going to print out the runtime. So first we need to calculate the stop time. So stop equals MPI W time. Then we're going to calculate our runtime. So double runtime equals stop minus start. And then we're going to print F. Total runtime is percent F seconds runtime. If you want this in milliseconds, you need to divide runtime by 1000. So if you wanted to do this in milliseconds, it would have to be runtime divided by 1000. 0.0. I'm gonna revert that back to seconds. If you want it to be in milliseconds, you can just divide by 0. No, not divide by 0, divide by 1000. Okay, so now it's ready. However, there is one other set of changes that are optional. It's optional because it's a bit more involved, and if you do go forward with these changes, you're now able to run your program for even more darts, but it's going to take more time to run. And these changes are for making the program throw more than 2 billion darts. You see, the program produces a better estimate for pi the more darts you throw. But we're limited to how large a 32-bit integer is, which is 2147483647 darts. If you want to throw more darts, you'd have to convert certain variables from their 32-bit version to their 64-bit version. There is some nuance to that, and I'll talk about it really quick right now. So all of these changes I'm going to talk about are optional. You don't have to do them, but I'm going to show you what that looks like right now. First, we need to include standard int.h. And this is because Well, the textbook says we have to use a data type called long, or maybe it's long, or maybe it's long int. That's problematic because the size of a long, and by extension a long, is platform dependent. So on some systems it's 32-bit, on other systems it's 64-bit. We want something unambiguous, and that unambiguous data type is called int64t. So, what variables are we to convert to 64-bit? Well, all the ones that have to do with our dart throws. So that is local darts within dartboard. That is int64 underscore lowercase t. And again, this is unambiguous. Unlike something like long or long int, it is going to be 64 bits long no matter the system. So I'm just going to copy this keyword here, paste it here, here. So your local and total darts within dartboard and to throw. Local darts within dartboard, total darts within dartboard, total darts to throw, local darts to throw. Also your remainder, if you calculated the remainder like it's been calculated here, you also need to change that to data type int64t. What else do you need to change to data type int64t? This I here. So, because this is counting to a value that's potentially greater than the 32-bit signed integer maximum, so we have to also change that one. So we're ready. Not quite. Your reduce operation here has the data type MPI int, but now we're working with 64-bit integers. So we need to swap this out for MPI int 64 underscore t. If somehow this is not supported, replace this with MPI long. Again, all these changes are just to make sure that no matter what system you're running this program on, the word sizes are unambiguous. It's also good practice this way too. Finally, we have a few integer variables being printed out. Now they are 64-bit. So to make sure that these variables are printed out properly, we can't use %d because that's for 32-bit variables. We need something else, and that something else is found in this include library here. So include int types.h. So much like how 64-bit integers may have varying keywords, the way that longs are defined may vary between system to system. The specifiers used for printf will also vary as well. It might be LLD or it might be something else on Windows. For something totally unambiguous, let's use this. And it's a little bit tricky to type out because it includes quotation marks. It looks a little bit weird, but it's % quotation mark space capital P capital R capital I lowercase d 64 space quotation mark. So any instance of us printing out a 64-bit integer, we replace %d with quotation mark space capital P capital R capital I lowercase d 64 space quotation mark. Okay, and again, all of these instructions are in the instructions here too. So let's just double check to make sure that I have all the required stuff here. So we have standard int.h for our unambiguous data type for a 64-bit integer. We have int types for our specifier for printf. We have changed all the required variables from 32-bit to 64-bit. And we swapped out the appropriate %ds with the appropriate %quote space print 64 space quote. And we swapped the data type for MPI reduce from MPI int to hopefully MPI int 64t. And again, this is just to be absolutely sure that no matter what platform your program is running on, it will work without any sort of ambiguity between word sizes. And once again, all of these changes from 32-bit to 64-bit are optional. You don't have to do this, but if you want to try the program with even more darts, then this is what you have to do. Okay, so let's compile our program to make sure we wrote it right. So the command to compile is as follows. MPICC-G-wall-O, the name of the program, the name of the source code file, and because we are using the math.h library, -lm at the end. So let me just make sure you get all that. That is the command to compile the program. Let's press enter to make sure it works. Press enter. Okay, so there is another thing that we had missed, so let's just double check that. Total darts within dartboard, and that is on line 71. Total darts within dartboard is, oh, there we go, print 64. Let's try it again. Now it is saying %LD, but again, that might, the word size might vary from system. The specifiers will vary from system to system. Let's just make sure we are totally unambiguous and use print 64 instead. Let's recompile that. Okay, it worked. Right, now we know it works. Let's try it out. Let's try one round of benchmarking. So the command to compile is MPI exec -n. Let's do 4 processes. I don't need the oversubscribe tag, not yet at least. /pi2 because that's the name of the program I specified, and let's do 1 million darts. Press enter. And we got our runtime in seconds. So our program is working the same as before. It is now working with 64-bit integers, which again is an optional change. It's now printing our runtime, so we don't have to rely on the time command anymore. If I do that, we get about the same time. Actually, there's just some little discrepancies, but yeah. Or let's use the time from this. Let's use the time from yeah, we're gonna use the time here. So there's some discrepancies with this one here. So anyway, now that our program is working, we can start benchmarking. So, much like before, you are to fill out a table of runtimes. 1 process, 2 processes, 4 processes, 8 processes. 16 processes with 1 million, 10 million, 100 million, and 1 billion darts. Let's try this. So when you begin your benchmarking, you're going to start with one process and 1 million darts. You're going to progress to 2 processes, as so, then 4, then 8. If you have the hardware, you can go even beyond and go all the way to, say, 32. And if you have the time and patience, you can go even higher with your dart count. So this is 1 million darts, 10 million, 100 million, 1 billion, 10 million. No, 10 billion. So let's try it with one process and see how long it takes. So this is the program running with one process, throwing 10 billion darts. Of course, it's going to take some time because that's a lot of darts to drop. Yeah, we're going to have to wait since this might take a while. Well, that took a while. Runtime was 470 seconds. So in theory, if I ran this again with, say, 6 processes, because that's the maximum I'm allowed to run on this system, well, let's do 8 processes, and I'm gonna force it to oversubscribe. Remember, if you run out of slots, just add the oversubscribe tag. You might not get any more performance out of it, however. So, keeping in mind that it ran for 470 seconds with one process, we should see a decrease with 8 processes, even though it'll probably only run 6 at a time. Let's try it. So now we have each process as seed. Again, each seed is unique to each process, just to make sure every process has a different seed. Because if you're using srand and rand for your random number generator, it isn't truly random because you have to pass in a seed. That makes it deterministic. That means if you use the same seed between runs, we are going to get the same sequence of random numbers being generated. That means we're going to be throwing the same darts. Oh, by the way, let's look at our estimate for pi. We have 3.1416. Yeah, it's 3.14159, but you rounded up. So yeah, we are getting a better estimate. So now, let's wait for this 8 process run to complete. Okay, so with one process, it took 470 seconds, and if we do the math, let's see. It took nearly 8 minutes just for the one process case to finish. However, with the 8 process case, which probably isn't truly 8 processes because I had to oversubscribe, it took about 100 seconds, so just under 2 minutes. That means you gotta speed up. So yeah, that is what we're trying to measure for. How much of a speed up are we getting by parallelizing this work here? We're throwing millions, maybe billions of darts at several dartboards, and we want to get an estimate for pi for that, from that. So that is the work of your benchmarking. You're gonna populate this table for the number of darts and the number of processes. One process, 2 processes, 4 processes, 8 processes, 16 processes, and then you repeat it for 10 million, 100 million, and then 1 billion darts. Next, you're going to take the values from this table and compute your speedups. How much faster is it to run with 4, 2, 4, 8, and 16 processes? So technically this is supposed to be, the optimal is supposed to be 6 processes, but I force it to run with 8. But it was still faster. So if we went with this example, how much faster is that? Well, if you divide 470 by 100, it's almost 5 times faster. So yeah, that is a significant speed up. So at this point, we are getting long runtimes on the order of minutes. And by parallelizing it, we still get a runtime on the order of minutes, but it is still running faster. So that is part 2. Part 3, you have 7 questions, and 2 of them are optional. And they are the same questions as before. Where do you think the sweet spot is for process count? Where do you think the sweet spot is for workload size? Do you think this was a worthwhile speed up? At what point did you stop seeing any speed improvements? And how would you compare your experience with programming with MPI compared to pthreads and OpenMP? Question 6 is adding extra columns if you have the hardware to support it. So you can add an extra column for 32 processes. And question 7 is also optional. You can add an extra column for 10 billion darts. Again, do this if you're willing to wait for that long to get those kinds of results. But I would wager that if you had the hardware for running 32 processes at once, and you tried it with 10 billion darts, it might just run even faster. Okay. Oh yeah, and all the instructions for the optional 64-bit changes are also in here. Once again, you don't have to do any of these, only if you want to and you can spare the time needed to run your program for that long. Okay. Now I am going to switch over to Visual Studio to show you what it would take to run it on a Windows machine. So this is just a rehash of the previous videos where I showed you how to run MPI programs on a Windows machine. Let's just name it PySMA program and create. Now let's create our source file. New item, CPP. So let's call this main.cpp. And I already have the code written out here, so I'll just paste it. Nothing's making sense because all the MPI related stuff isn't recognized yet, so I have to undergo this multi-step process of telling the program, hey, I'm working with MPI. So let's save that for now. Let's right click here and select properties. And now let's proceed with those steps. Okay, so go to C/C++ over here, expand this dropdown, expand this menu over here. Actually, no, we click on C/C++ and add additional include directories. Click this dropdown, edit. Now we want to add we have to go to our folder that contains our include directory. So if you had installed those 2 installers, go to your C drive, because that's where it's this installed by default. Program files x86, Microsoft SDKs, MPI, include. Select folder. Click OK. Click Next on Linker. Additional library directories. Click on that. Click the drop down. Click Edit. Let's add. Now, this next step is going to depend on whether your program is being built for a 32-bit machine or 64-bit machine. So it's configured to x86, that's 32-bit. So I want the 32-bit library folder. So let's go back to the C drive, program files x86, scroll down, Microsoft SDKs, MPI, lib, x86, select folder, click OK. We're not done yet. There's one more thing we have to do. Under Linker, expand this, click on Input, click Additional Dependencies, click Edit, and just type in msmpi.lib. Press OK, click Apply, click OK, and all of our errors are gone. That means now we are ready to go. Press Ctrl-Shift-B to compile your program. Initializing conversion from time t to int, possible loss of data. Ignore that warning for now. So, it now says build succeeded down here. That means now we can right click here, open in File Explorer. Go in the debug folder. No, not that one. We actually have to go back one directory. So click this up button here in Windows Explorer. And we want this debug folder. Enter that, and there's a program. Type PowerShell in the address bar. Press enter, and it is the same command to compile as it was with our Linux system here. With the one difference being, I have access to all 16 cores on my Windows machine. So, let's try it out. MPI exec -n. Let's do one process and 1 billion darts. I have to type the name of the program. So MPI pi estimating program .exe, and then 1 billion. Press enter. Now we wait. Actually, no. I'm gonna abort that, and let's do a more tame 1 million darts first. And there we go. It worked. Now, let's try a larger number of darts, say 10 million. Of course, it took longer. What if I ran it again and did 16 darts? Because I have access to all 16 cores on my Windows machine. Press enter. It ran the program in a fraction of the time. So in theory, you'd expect this to be 1/16 the time as the one process case, but that might not necessarily be the case because of overhead from message passing. So if I am to run this program on my Windows machine, these steps are a little bit different, but I can access all 16 cores on my machine compared to running it on my virtual machine here. The reason why I have all the instructions primarily centered on a Linux machine is because it's far easier to compile. But in the past, I have taught this course using a Windows machine, but now I'm just gonna have both options available from here on out. Alright. Even though the setup for a Windows machine is a bit more involved, at least for me, if I run these programs on my Windows machine, well, let's just say I bought this CPU, I'm going to use the whole CPU. Alright, so that is your final project. It's benchmarking, but it's just one more round of benchmarking. So, benchmark your program, fill out the table, answer the questions, and that's it. That's the whole course. If you made it this far, pat yourself on the back because we did it. Hopefully you have learned why it's important for us to parallelize programs and what it takes to parallelize programs and what kinds of results we get by doing so. So, yeah, that's it. That's the whole course. I hope you had a good time learning about parallel programming with me, and yeah, I guess I'll see you all later. Until again. One more thing. I will be grading the last of your assignments in the coming days, so watch out for another announcement where I announce, hey, I've graded everything, make sure everything looks good, okay? Okay. Until again.